Assalamu alaikum everyone. Welcome to the 13th lecture of our course. Today's topic is Simpson's one-third rule and Simpson's 3/8 rule of integration. Okay, so we'll learn about these two numerical methods of integration in today's lecture. So the plan for today is to understand the basic concept behind the rules of integration that were proposed by Simpson, and we'll understand some of the derivation approaches of the Simpson's one-third or Simpson's 1/3 rule formula, and we'll derive the multiple segment version of the Simpson's 1/3 formula. Okay, and then we'll do the same things for the Simpsons 3/8 method of numerical integration as well. And lastly, we'll understand how these two methods can be merged together as a fused algorithm. Okay, and we'll see how we can apply that fused algorithm on an example. And for today's lecture, you'll be able to see some text dagger sign, which basically looks like the Christian cross, right? So you'll be able to see some red text dagger symbols besides the heading of some topics, and those topics. This text dagger symbol basically signifies that those topics are not that important for your exams. Okay, if you are finding it hard to maintain uh, your preparation time, or if you're finding it hard to finish your preparation within time, you can choose to skip those topics. Okay, but for the sake of completion, we'll discuss it in the lecture. Okay, so what are Simpson's rules? So there was a British mathematician called Thomas Simpson. So he proposed some. He came up with, or basically invented, some numerical integration methods, and those methods are basically named after him, and they are called the Simpson's rules of integration. Okay, so what's the idea? So back in trapezoidal rule, what did we see? We saw that we used a first order polynomial or a straight line in order to approximate the area under a curve, right? So if our function was, on our curve was f of x, we basically drew, let me show you over here. So we basically drew a straight line that went from the upper limit to the lower limit's functional value, and we told that, okay, the area under this area that is being occupied by this trapezoid will be approximation of the area under the curve. So it looks very bad, right? It's a very bad approximation of the area under the curve. So what Simpson did is, instead of taking a first order polynomial as the polynomial that's approximating the behavior of the original function, he took polynomials that were of order greater than 1. Okay, so n has to be greater than 1 for an nth order polynomial. So today we'll discuss about two of the most basic Simpsons rules, which are the Simpsons one-third rule and the Simpsons 3/8 rule. Okay, they're also called the Simpsons 1/3 rule and Simpsons 3/8 rule. So in the case of Simpsons 1/3 rule, we use a second order polynomial in order to approximate our original function. And for our Simpsons 3/8 rule, we use a third order polynomial. Okay, so it's denoted using f sub 3 of x. Okay, so we'll learn about them in a bit. And today we'll also discuss about how these two rules can be combined together. Okay, together we'll use them in order to solve an example. Fine. So those are, a long story short, what Simpson's rule mean. Okay. So let's discuss the first version of the Simpsons rule, which is the Simpsons 1/3 rule. So the idea is to let me switch over to the laser pointer. Okay, so the idea is to approximate an integral of a function, or the integration of a function with respect to dx from the lower limit a to the upper limit p, using a second order polynomial. Okay, so suppose you have this f of x function, original function. So it may be a very complicated function, right? It can be a very convoluted, the equation or the expression that the function is, can be very complicated or very convoluted. It might have transcendental functions within it, right? So in order to capture the behavior of this function, we'll use a polynomial. Okay, so why are we using polynomials? Because polynomials are, as we know, very simple to integrate, right? You can write up a program to integrate any type of polynomials, in very few lines of code, right? But it's not the same. The case is not the same for other types of functions, right? Because in order to integrate those functions, our code will become suddenly it will become very large, right? Because we have to take care of a lot of cases, right? So the idea is to approximate the original function using a polynomial of a certain order. So in Simpson's 1 by 3 rule, we do that using f sub 2x, okay, or it's also called a second order polynomial. So the general form of a second order polynomial is something like this: a naught plus a1x plus a2 x squared, right? And so how do we approximate the polynomial? If you recall, so if we have n plus 1 data points given to us, we can draw a nth order polynomial that passes through all of those points, right? So in order to come up with a second order polynomial that we want to use in order to approximate f of x, we have to take what, three equidistant points, right? That is on top of f of x, right? So let's say in order to take three equidistant points, what do we have to do? We have to basically divide the whole span of this function into two segments, right? So one segment is from a to the midpoint, and another segment is from the midpoint to the upper limit, right? Or from b or to b, right? So what's the middle point? We know that the middle point between two limits a and b is a plus b by 2, right? Because the span of the interval is b minus a, and if we divide b minus a by 2, we get what, b minus a by 2, obviously. And if we add b minus a by 2 to a, which is the upper limit, sorry, which is the lower limit, we get the middle point, right, which is a plus b by 2. So we'll see how we can come up with a formula that basically calculates the area uh, under the second order polynomial in order to approximate the actual integrand, which is the area under the f of x curve. Okay, so let's see how we can do that. So before starting to talk about this slide, just I'd like to draw your attention to this text dagger sign over here. So whatever derivation we will discuss for this formula, that requires some equation solvers. Okay, these derivations are very broad or time consuming to do using pen and paper. So we resort to symbolic equation solver softwares like MATLAB, Octave, Maple, and Wolfram Alpha. Okay, so obviously these type of derivations are not important for exams, but for the sake of completion, I'm including it in the lecture so you guys get an idea how the actual formula is being manifested. Okay, so let's discuss about this. So we have the original, we have the general form of the second order polynomial, which is what, f sub 2 of x equals to a naught plus a1x plus a2x squared, right? Now we have three unknowns, a naught, a1, and a2. These are the three unknown coefficients of the parameters of this polynomial over here, right? So you have to somehow come up with these three unknown values, so such that upon plugging them to the second order polynomial equation, we'll get such a second order polynomial which basically resembles the pattern of the original function f of x. Okay, so let's see how we can do that. So in order to in order to come up with the values of three unknowns, we need to come up with three equations, right? So how can we do that? So we know for sure that our polynomial p of x, let's say, or f sub 2 of x, is for sure passing through these 3 points, right? So the first point is what, a comma f of a, right? So this point over here, this coordinate over here is a comma, the abscissa is a, and the ordinate is f of a, right, the functional value of a. So the coordinate at this point, the data point over here, is what, a plus b by 2, which is the ordinate, the x value, and the y value is what, f of a plus a by 2, right, the functional value at this point. And the last point is the functional value at the upper limit, right? The upper limit is b in this case. So we have these 3 points, a comma f of a plus b by 2, comma f of a plus b by 2, and b comma f of b. So we know for sure that the polynomial passes through these 3 points. So what we can do is we can use that information and come up with three equations, right? So we know that f of a equals to f sub 2 of a. So this is the same point, the original function and the polynomial both pass through this point. So you can say that one equation is a naught plus a1 times a plus a2 times a square, right? Because we are just simply plugging in the value a or the symbol a in the place of x, right? So we had originally x. Now we know the value of x to be a, so we just plug in the value a over here. We end up with one equation, right? So let me mark it. So we say we have one equation over here, And again for the second and the third data point, so which is the this point over here and this point over here, these 2 points. So we have already dealt with this point, right? We come up with what? Second equation and the third equation, right? So what we can do is, okay, now that we have ended up with three equations over here, we can solve these three equations, right? So we can solve these three equations to come up with what? Three of our unknowns, right? So you can choose to do it using pen and paper, using say substitution or elimination, but it will take a huge number of steps and a lot of time to come up with the actual symbolic values of a naught, a1, and a2. So what you can do is you can basically form the matrix. So we know how to form matrix from equations already, right? So after forming the matrix, you just give those matrix to the symbolic solver software like MATLAB Octave, and they will basically return you the actual equations or the values of the unknowns in terms of these symbols a, b. Okay, so in terms of these symbols a and b and functional values of those a and b. So what we end up with is for a naught we end up with this huge equation expression over here. For a1 we end up with minus this whole expression over here, and for a2 we end up with this whole expression over here. Okay, so if you so for these three you don't need to memorize them or learn them by heart, because as I've said before, this slide over here is not important for your exam, but it's important to understand how the actual formula comes. Okay, so we'll talk about the actual formula in the next slide. So up to now we just came up with that second order polynomial that approximates the original function f of x. Okay, so how did we come up with that? We came up with the coefficient values or the parameter values by solving these three equations. Now that we know the a0, a1, and a2 values, we can simply what? We can simply plug them in, right? We can simply plug them into our second order polynomial, general version of our second order polynomial, which is this one, and we get something like this. So before plugging in, what we can do is we can integrate. Okay, since in its simplest form it's very easy to integrate this polynomial, let's integrate this polynomial from the lower limit a to the upper limit b. So what we can do is, okay, we know the integration of a naught with respect to dx is what? A naught x, right? For a1 x it will be a1 x squared by 2, and for a2 it will be a2 times x cubed by 3, and the value ranges from a to b, right? Now we just plug in the respective values b and a. So what we get for x, we get b minus a. For x squared by 2, we get b squared minus a squared by 2. And for x cubed by 3, we get b cubed minus a cubed by 3. Okay. Now that we have, in the previous slide, we have derived the formulas or come up with the formulas of, for not formulas, the expressions for a naught, a1, and a2. We can simply plug in these three huge expressions in these places over here. Okay, a naught, a1, and a2, and we substitute them, and we get this after a series of multiple simplification steps. We end up with this formula over here. So these simplification steps have been left out of this slide for brevity, because as I've said, the slide has been marked with this text dagger symbol, right? Because this is not important for your exam, so I have left out the intermediate steps for the purpose of brevity. Okay, so you can trust me that what we end up with is this whole thing over here. Now we know that our, let's go back to the figure, we know that our span is b minus a, right? This from the upper lower limit to the upper limit, right? And we know we have separated this span over here, or this interval over here, into two segments to equal these segments, right? Because we have chosen equidistant 3 points, right? So the interval has been divided into two segments. Now each of this segment, the width or the what in Bangla we call it prostho, right? The width of each of these segments is what we call it the step size. Okay, and the step size is denoted using the small letter h. And since we have taken two segments for the Simpsons 1 by 3 rule, we take two segments. Okay, so single segments, Simpson 1 by 3 rule breaks the entire interval from the lower limit to the upper limit to two smaller segments. Okay, so since we have the whole interval divided by 2, we say that the step size is b minus a by 2. Now what we can do is, since in the formula that we have come up with after substituting the actual expressions for a naught, a1, and a2, we can simply say, okay, we can rewrite b minus a by 6 as what? H by 3, right? Because b minus a by 2 is h, so h by 3 will for sure be b minus a by 6. Simple algebra, right? Simple arithmetic. So we can rewrite this whole formula as, okay, the approximation of the area under the curve f of x, which means the integral of the function f of x with respect to dx from the lower limit a to the upper limit b is approximately equal to h by 3 times f of a plus 4 times f of a plus b by 2 plus f of b. Okay, so this whole formula over here is called the Simpson's 1 by 3 rule. So I have already mentioned that the derivation process is not important for your exam, but you have to learn this formula by heart. Okay, you have to basically after practicing the relevant maths multiple times, you should already you should be able to uh, basically try to recall it from memory, okay, if needed, inshallah. So try to practice the relevant maths. We'll discuss a simple example in an upcoming slide in a bit, so wait for that. And about the derivations, if you're interested, you can go through the actual lecture note pdf that I'll be providing as an accompanying uh, as an accompanying attachment with this slide. You can go through that lecture note by Professor Author Kaur, and you can basically learn about the other methods of derivation. So in back in our trapezoidal rule of integration, we have learned about four methods of deriving the actual trapezoidal rule formula, right? So we can do the same thing for the Simpson's 1 by 3 rule as well. So you can do it using the NDD or the Newton's divided difference polynomial. You can do it using the Lagrange version of the second order polynomial. You can also do it using the, as far as I recall, using the coefficient method. Okay, so we learned about the coefficient method of derivation in our trapezoidal rule. We can do the same thing for our uh, what Simpson's 1 by 3 rule as well. Okay, so if you're interested, you can go through these other three methods of deriving the actual Simpson's 1 by 3 formula. But other than that, it's not important for your exam. Just try to remember the actual formula itself that has been bounded by this blue box over here. Okay, fine. So let's try to solve an example. Let me switch back to the laser pointer. Let's try to solve an example using the Simpson's 1 by 3 formula that we have just derived. So the example is very simple. So let's ignore this integration sign for now. This whole function over here, this is the velocity function of a rocket. Okay, so the rocket follows this behavior of this function when it is launched, okay, from say a station to space. Fine. So we know that the integration of a velocity function is what? The distance covered by a body, right? So the distance covered by this rocket from time t equals to 8 seconds to time t is equals to 30 seconds is the integral value of this thing over here. Okay, this integral value of this function over here from the lower limit 8 to the upper limit 30 with respect to time, obviously, with respect to dt basically. So we are denoting the integrand value as x over here. Okay, the variable is t over here, mind it. So firstly, we'll use the Simpson's 1 by 3 rule to approximate the value of the integrand, obviously, and then we'll compare it with the actual value of the integrand and find out the true error. Okay, so we know the true error is denoted using capital E sub t, and we'll find out the absolute relative true error, which is the absolute value of the epsilon sub t. Okay, let's see how we can do that. So we have already derived this formula b minus a by 6 times f of a plus 4f of a plus b by 2 plus f of b, right? We know the value of a to be what? 8. We know the value of b to be 30, right? So we know these two values. We know the midpoint between them as well, which is a plus b by 2, which is 19, right? Fine. So now that we know the function, we know the upper limit and the lower limit and the midpoint, we can basically plug them into the formula, right? So before plugging them into the formula, we need to find the respective functional values. Okay, let's do that at first. So we know the original function is this, f of t, with the velocity function is this, 2000 times natural logarithm of what 140,000 divided by 140,000 minus 2100 t minus 9.8t. Okay, so at the at the lower limit, which is a, which is 8, the functional value is 177.27 meters per second. At the point 30, which is the upper limit, it's 901.67 meter per second, and at the midpoint 19, it's 484.75 meter per second. Okay, you can simply find these out using a calculator. And after we have found these three functional values, what we can do is we can simply invoke the formula that we have derived, this formula over here, and plug in the values to the respective places. So for b we plug in 30, for a we plug in 8, for f of a we plug in the value of f of 8, which was this. For f of a plus b by 2 we plug in the value of f of 19, which was this. And for f of b we plug in the value of the upper limit, the functional value of the upper limit, which is f of 30, right, which was what, 901.67 meter per second. And using a calculator you'll end up with this value over here, which is 110 sorry what 11,065.72 meters, which is the distance covered by this rocket in approximation, an approximate value of the distance covered by this rocket. Okay, so what you can do is, if you have the time, you can analytically try to come up with the exact value of this integration over here. You'll see that the value comes to 11,061.34 meter. Okay, when solved analytically, this is the exact value. So now that we know the true value, we can find out the true error, right? Which is simply the difference between the true value and the approximate value. The approximate value we have already deduced, which was this. So we take the difference, we find it to be what, minus 4.38 meters. Okay, this is the true error, and the relative absolute relative true error is this value over here divided by the true value, the absolute value of that thing, times 100. Okay, and it comes with a and it ends up being a very minuscule percentage of 0.0396%. Okay, so if you compare this absolute relative true error with the absolute relative true error of the trapezoidal method, you'll see that the Simpson's 1 by 3 rule is sufficiently better approximation compared to the trapezoidal rule of integration. Okay, so it's obvious because instead of using a straight line, we're using a second order polynomial to approximate the behavior of the original function. Okay, which was this whole thing over here in this specific example. F of t equals to 2000 times natural logarithm of 140,000 divided by 140,000 minus 200 2100 t minus 9.83. Okay, so now that we have seen the single segment version of the Simpsons 1 by 3 rule. So mind it, so when I say single segment, I mean that we are considering a single second order polynomial to span the whole interval from A to B. Okay, so the whole single segment is being divided into, or subdivided into, two smaller subsegments. So two smaller segments we call it. Okay, so try to understand the nuance between the segment and the smaller segments. Okay, when we say single segment 1 by 3 rule, we mean that, okay, we'll take three equidistant point, and we'll use one f sub 2 of x, or one second order polynomial that will try to approximate the behavior of the function f of x between the uh, lower limit a and the upper limit b. Okay, it will obviously be valid between a and b only. Okay, not in other ranges. Fine. So that now that we know the single segment version, we'll talk about the multi-segment version of the Simpson's 1 by 3 rule. So what you can do is, so you're obviously seeing this GIF over here. I took this GIF from this YouTube video over here. So if you are a fan of the simulations of three blue one brown YouTube channel, right, very good YouTube channel, so there is a similar type of video on this topic over here. You can click on this link and watch it. Very simple to understand, and this is the GIF version of that video. Okay, so before delving into this GIF over here, we'll try to understand the concept behind the multi-segment Simpsons 1 by 3 rule. So before, what we did was we only used one single second order polynomial in order to detect the pattern of the whole curve, right? But now we are not resorting to only one second order polynomial. Okay, we'll resort to two or more second order polynomial, and whatever the value of the, or the number of the polynomials that we want to end up with, or that we want to use, that has to be a multiple of 2, or it has to be an even number. Okay, so we'll try to let's try to explain why that needs to be even. So it's very obvious. So let's go to our demo paper and see how it works. Okay. Okay, so now that we are here, okay, so let's try to draw a curve at first. Let's say these are my axes, the Cartesian coordinate axis, and let's say my curve looks something like this. Okay, so our target is to find the area under the curve from this lower limit to this upper limit right here. So let's say this is A, and let's say this is B. Okay. So previously, what we did was we found a midpoint, right? So we took these 3 points and we drew a second order polynomial between them, which looks something like this. Let's say it will look like a quadratic function, obviously. So then we measured the area under this curve, and we said that okay, that area is an approximation of the area under the original function. Okay, so let's say this was our original function f of x, and this was our f sub 2 of x. Okay, so let's undo this whole thing because we have already learned about the signal segment of version of the Simpsons 1 by 3 rule. Now we'll see how we can do it using multiple segments. So let's say, okay, instead of using a single segment, we'll use multiple segments because that obviously makes more sense, right? Because what we saw was, okay, let me undo it. So what we saw was what a huge error over here, right? So even though this part may cancel each other out to a great degree, we want to avoid our error, our truncation error as much as possible, right? So let's see how we can do that. So instead of using a single second order polynomial, okay, so why not use multiple segments? So let's say, okay, let me divide this whole span into two equal segments, okay, which means we will of course do it along the midpoint. Let's say it looks something like this. Okay, roughly this is the midpoint. Now what we'll do is we will perform the single segment uh, Simpsons 1 by 3 rule on this segment and on this segment separately. Okay, then what we'll do is we'll add them up together and we'll say that okay, so this addition over here is my approximation of the area under the curve. So let's see how we can do that. So we know for applying the Simpsons 1 by 3 rule, we need to find out the midpoint, right? So the midpoint, so we are treating these two intervals separately, right? So this interval and this interval is being treated separately in the case of the multiple segment Simpsons 1 by 3 rule. Okay, so okay, first let me draw the midpoints. Let's use a different color. So this is a midpoint. So for this sub interval over here, this is the midpoint, right? So roughly I'm basically eyeballing it. Okay, so this is the midpoint over here, and for this segment over here, let's use a different color. This is the midpoint over here, right? Roughly speaking, for this sub interval over here. Now let's try to label these segments. So for more clarity, we'll label this segment so you can keep track. So this initial or the lower limit, let's call it x naught. This is the first value of x. So let's call this the x1 point. This is the right hand side of the first segment. Let's call this thing the x2 point. Let's call this the x3 point, and let's call this, we can simply say okay, this is x4, right? So we have divided our whole area under the curve into what, 1, 2, 3, 4 partitions, right? Okay, now what we'll say is okay, now we'll apply Simpsons 1 by 3 rule separately on each of these segments. Okay, so what we can do is okay, let's try to come up with a second order polynomial. So for this segment, so from a to x2 or from x0 to x2, we can say okay, the polynomial that passes through these 3 points, or the second order polynomial that passes through these 3 points, may look something like this. So it's roughly of the shape of a parabola, quadratic function, right? Let's say it looks something like this. And again, we'll say okay, now that we know the parabola or the quadratic function or the second order polynomial that passes through these 3 points, we can say okay, the area under that approximation curve or that polynomial may look something like this, right? So that right there, or this section or this area marked with blue or shaded with blue, is the first half of my approximation. Okay, and for the second half of my approximation, what we'll do is we'll come up with another second order polynomial. Okay, so for another second order polynomial, let's use red. So okay, so we know this is a this curve. So let's say we are using these 3 points, this point, and this point. Okay, these 3 points in order to come up with another second order polynomial. Let's say it will roughly look something like this. Okay. So, okay. So now that we have come up with our second order polynomial using our second set of consecutive segments, we can say, okay, the area under this polynomial, second order polynomial within the limits x2 to x4 is this red shaded region, right? Now, if we sum up the blue shaded region and the red shaded region, the area, the summation or the aggregate of the area that we end up with, we say that okay, that area is uh, good enough or a better approximation of our area under the original function, right? Original f of x function, which was drawn using this black ink, right? And this is our first f by 2, f sub 2 of x, and this is another, say, f sub 2 of x, or a second order polynomial. Okay, fine. So using these two separate second order polynomials and calculating the area under them or finding their integrand within the suitable limits, we said that okay, if we sum them up together, we end up with an approximation of the area under the original function f of x. Okay, so this is, long story short, the concept behind, or the idea behind the multiple segment Simpson's 1 by 3 rule. Okay, so this is the simplest case, which was done using two segments. Okay, so you can obviously scale it up to three segments, four segments, and whatnot. So whatever we do is, sorry, using not using two segments, using two uh, second order polynomials, right? So if we use two second order polynomials, you're working with four segments, right? So one, two, three, and four segments, right? So you can of course scale it up to six segments, eight segments, and whatnot. Because, so let's talk about why the value of n is being even, because we are working with two consecutive segments, right? For each application of the Simpson's 1 by 3 rule, we need two segments, right? So we need two adjacent segments or two consecutive segments. So whatever the total number of segments cannot be odd. Okay, it has to be even so that we can properly apply the Simpson's 1 by 3 rule for over the span of these two segments. Okay, so for in the first case it was from the span or within the interval x naught to x2, right? In the second case it was from x2 to x4, right? Fine. So now that we know why the value of n should be even, let's go back to our presentation and try to come up with a compact or a closed form formula for this multi-segment Simpson's 1 by 3 rule. Okay, we try to derive it. Fine, let's go back. Okay, now that we are back to the presentation. Okay, so before delving into the derivation, let's try to talk about this GIF over here. So in the style of 3 blue, 1 brown, fluid visualization of this multi-segment Simpson's 1 by 3 rule is in this GIF over here. So what you can see is that we are working with two consecutive segments, right? So in each of, within these two consecutive segments, we are using what? Three equidistant points, right? And using these three equidistant points, we are trying to come up with the second order polynomial. So every triplet of the point is coming up with a second order polynomial, and the area under those polynomials is being added up in order to approximate the area under the whole curve. Okay, so the whole original curve was this red line over here, and these second order polynomials are being drawn using this say what, purple violet colored lines, right? Okay, so this was for what, when the step size is 1. So this is when the step size is zero point 0.5, the segment widths are narrower, so we are ending up with more segments, right? So the more the number of segments, we know that the better our approximation becomes and the lesser our error becomes, right? As we have seen from the trapezoidal rule. Okay, so let's now try to and the uh, formula for the step size is similar in the case of multi-segment Simpson's 1 by 3 rule as well. It's the whole span, or b minus a, divided by the total number of segments, which is n. And we know for sure the value of n is odd. Okay, so the value of n is even, my bad, the value of n is even. And in order to watch the whole video, you can click on this link over here, highly recommended. Okay, now let's try to talk about the derivation. So what we saw from our trapezoidal rule is that in order to come up with the area under the curve f of x, what we did was we summed up the area of the segments, right? We did we'll do the same thing for the multi-segment Simpsons 1 by 3 rule as well. So try to understand. Okay, let's go back to the bamboo paper and try to understand this thing over here instead of speaking about it in the presentation. Okay. Okay, now that we are back, let's go to a new page and try to see the general case of this multi-segment Simpsons 1 by 3 rule. Okay, let's try to draw another curve. So let's try to draw a curve that is similar to the example we just used before. Let's say it looks something like this. Okay, so we'll try to approximate the area under this curve. Okay, so we'll use our lower limit will signify or symbolize it using the value a, and our upper limit will be the value b, and our target is to find the area under this curve. This is the original function f of x. Okay, fine. So what we can do is, okay, we know in our multi-segment trapezoidal rule, what we do is we partition the whole area under the curve into multiple segments, right? And in the case of multi-segment Simpsons 1 by 3 rule, we saw that the number of segments had to be, we have to make sure that the number of segments that we choose is an even number or is a multiple of 2, right? So let's do that. Let's try to see the general case. So let's say this is one segment, this is another segment, this is another segment, another segment, another segment. So there's, let's put it, let's put ellipses between them and say, okay, there are numerous other segments in between them. And let's try to draw the last few segments, which looks something like this. Okay, so fairly accurate. Okay, fine. So our let's try to denote our lower limit as x naught right now. So let's say this is x naught. So this has to be x1. This is x2, and so on up to what we have. So this will be what x of x. Okay, this will be what? So this is xn. We know x minus 1. So this is xn minus 2, and this is xn minus 1. And we know the upper limit b will be for sure xn minus the x sub n, right? Because we are taking n segments where n is even. Fine. So now that we know the labels of each of our right hand sides of our segments, what we can do is, okay, we will take three consecutive points or two consecutive segments. We will consider two consecutive segments in order to come up with our second order polynomials. Okay, let's say, okay, we'll use the first 3 points, this point, this point, and this point, in order to come up with a second order polynomial that might look something like this. Okay, obviously this is not an accurate, just uh, what it should look something like this. No, obviously not accurate. Fine. Okay, so something like this, a quadratic function that looks something like this. So we say that, okay, we'll try to measure the area under this curve between the lower limit a or lower limit x naught to the upper limit x2. Okay, now we'll do the same thing for the next pair of segments, which is what? This segment and this segment, right? So for these two segments, we are considering this functional value point or this coordinate, this data point, this data point, and this data point, right? So between these three within these three data points, we have to uh, pass a second order polynomial, right? So it might look, say, something like this or something like this roughly, right? Something like this. Yeah? Okay, so let me draw it a bit clearly, something like this. Fine. So we say that, okay, we'll try to calculate the area under this curve, under this second order polynomial between the ranges, between the lower limit what x2 up to what, this is x3 of course, and this is x4. So a trend we'll be able to see is that the indices of the lower limits and the upper limits are always even, right? So from 0 to 2, from 2 to 4, right? And we'll continue these steps for all the consecutive pairs of segments, and we'll try to find the area under the curve. Okay, and for the last two segments it should look what something like this, right? So for the last two segments, we are considering this point, and this point, right? and the area that or the second order polynomial that approximates the pattern of uh, this part of this segment of the function is may look what something like this, right? So roughly something like this. Yeah, roughly something like this, right? So we'll try to measure the area under this curve between these limits, which is what x of n minus 2 up to xn, right? So x sub n minus 2 to xn, and we'll sum up all these areas. We end up with an approximation of the area under the original curve f of x. Okay, so to write it formally, we write it as something like this: our integrand value, which is the integration from a to b, the integration of the function f of x with respect to dx. So we can approximate this value using what? Write it a bit clearly. We can approximate this value as the approximation or the integration of an of a second order polynomial from the lower limit what x naught up to x2, right? Up to x2 plus the integration of another f sub 2 of x. So understand that this second order polynomial and this second order polynomial may not be the same. Okay, as we have seen from this figure over here, the sample figure over here, we are just denoting it to be the same, but uh, in practice it may not be the same. Okay, so from this the second for the second pair of segments, we come up with the second order polynomial that is valid between what from the range x2 to x4, right? So our lower limit will be x2 and our upper limit will be x4, right? And we can say we can put ellipsis here. The rest of the terms will follow a same behavior and say there is no space. Okay, let me write it as something like this. So let's go to the next line. So we can say okay for the second last pair of segments, understand that there is another segment over here. So this was what x of n minus 3 obviously. So this is x of n minus 4, and this thing over here is x sub n minus 3, right? Fine. So we can say okay our second last pair of segments has the area which is the integral value of another say second order polynomial f sub 2 of x with respect to dx between the ranges what x of n minus 4 up to, write it a bit clearly, up to x of n minus x of n minus 2. Okay, fine. And for our last segment, it looks something like this: another integration of another second order polynomial with respect to dx, and between the ranges what x of x n minus 2 to x of n, which is practically b, right? And we know our initial x naught, it was practically a, which was our lower limit, right? So this is kind of this whole summation is kind of an approximation to the actual integral value of the actual function, right? So what we can do is okay, we have a set of Simpson's 1 by 3 problems, right? So what we can do is we can apply the formula that we have derived in our simple case of Simpson's 1 by 3 rule, which was the one segment Simpson's 1 by 3 rule. We can apply that formula for each of these pairs of segments, right? So understand when I am reiterating, when I am using the term one segment Simpson's 1 by 3 rule, I'm indicating the non-composite version of the Simpson's 1 by 3 rule, okay, where we use only a single second order polynomial in order to approximate the entire function f of x, and we then find the area under the curve of that polynomial in order to approximate the area of the curve under the actual function. Okay, fine. So what we can do is okay, let's apply the formula. So if we recall, the formula looked something like, let's go back to the, I did not write it here, let's go back to the slide and see what the formula looked like. Okay, now that we are back to the slides, okay, the formula looks something like this, right? So h by 3 times f of a plus 4 times f of a plus b by 2 plus f of b, right? So we'll use this formula where we know our lower limits and our upper limits. We'll use this formula and see what how this thing how the actual formula pans out for the case of multi-segment Simpsons 1 by 3 rule. Okay, let's go back to our memo paper. Okay, so let's try to apply the formula for the first integral of the integral of the first second order polynomial. So for each of these, I forgot to write t of dx. Let me write them. So obviously, the second order polynomials are being integrated with respect to dx. Okay, so after applying the formula in this for this term over here, what do we get? So it's p minus a by 6, right? As far as that equals, so x2 minus our upper limit is x2 minus x naught divided by 6 times f of x naught plus 4 times f of the midpoint, right? So what's our midpoint? It's x1, right? Because the midpoint between x naught and x2 is for sure x1 because we are selecting equidistant points, right? So f of x1 plus this is what the last point is f of x2. Last point is x2, so the corresponding functional value is f of x2, right? Now for this segment, for this term over here, let's try to write the corresponding formula, which should look something like what, x4 minus x2. So let's write it below because obviously it won't fit here. So x4 minus x2 divided by 6 times f of x2 plus 4 times f of x. So between x2 and x4 we have x3, right, as the midpoint. So we have x3 plus f of f of x4. Fine. So now that we have this, let's proceed with the remaining terms. So for the intermediate terms, I'm putting ellipses or dot dots in order to for the sake of brevity. And for the last two terms, we have what? For this term over here, we have xn minus 2 minus uh, xn minus 4 divided by 6 times f of xn minus 4, obviously the lower limit. We write it a bit more legibly, xn minus 4 plus 4 times. So between xn minus 4 and xn minus 2, we have xn minus 3 as the midpoint, right? So obviously it will be xn minus 3 plus the final, the upper limit, which is f of xn minus 2. Fine. And for the last term, we have something like uh, this, right? So we have f xn, which is practically the same as writing t over here, xn minus xn minus 2 divided by 6 times f of xn minus 2 plus 4 times between xn minus 2 and xn, we have xn minus 1 as the midpoint, so xn minus 1 plus f of xn, which is our final functional value, right? This whole thing over here. Okay, now that we have applied the Simpson's 1 by 3 formula on uh, every single term of this expression over here, we end up with this whole expression. Okay, so what we can do is we can try to simplify this expression further in order to concise, maybe make it more concise and compact, okay, so that it becomes a formula that is easy to recall and remember. Okay, let's go to the next page and see how we can do that. So okay, so instead of going to the next page, let's try to utilize this space over here, so it will be easier to follow for you guys. So what we can do is, okay, so from here we are coming to here, obviously, fine. So now that we have seen, let's try to see what we can do with this line over here. So now that we know the distance between the lower limit of each pair of segments and the upper limit of those pair of segments is 2h, right? Because we know that for a, say, for a value of I where I is even, we know xi minus, sorry, xi minus 2 is equals to 2h, right? Because we know the width of each segment is h, and the width of two consecutive segments will therefore be 2h, right? So what we can do is we can replace x2 minus x naught with, let's use a separate color. Uh, we can replace x2 minus x naught with what, 2h. We can replace x4 minus x2 with 2h. We can replace x sub n minus 2 minus x sub n minus 4 with 2h. We can replace xn minus xn minus 2, so x sub n minus x sub n minus 2 with 2h, right? So what's happening here is that we are ending up with the fraction 2h by 6 in the front of our in front of each of these terms, right? So you can simplify it further and say, okay, so this thing becomes h and this becomes 3, right? So again this becomes h, this becomes 3, this becomes h, this becomes 3, this becomes h, and this becomes 3. So what we are saying is that, okay, if we take if we factor out h by 3, or if we take h by 3 as common, what we'll end up with is h by 3 at the front of our compact formula. Okay, so we'll write h by 3 at the front, and whatever other algebraic manipulation we need to do, we'll do it using inside this third bracket over here. Okay, now let's see what do we have remaining. So we have the first functional value at first lower limit x naught. We have f of x naught, and then we have what, we have 4 of f of x1, 4 times f of x1. We have okay, so try to uh, notice this pattern over here. What we can see is that the f of x2 is appearing once in this term, again once in this term as well, right? F of x4 is appearing once in this term, and again implicitly once in a term that is within this ellipsis, right? So in this ellipsis part over here, we have another term which starts with f of x4, right? Because of course we'll, for this say for these two segments, if we want to find the area here, we need to start with x4 and end at x6, right? So of course there is a term over here which starts with f of x4. So what we can see is that, okay, we'll have what, 2, in our compact version we'll have 2f of x2, then we'll have what, again we'll have 4f of x3, then we'll have as I've said before, 2f of x4, and we can basically put the rest of the terms as ellipses because it will gradually become redundant if we keep writing them. These terms over here are enough to understand the pattern. Okay, let's try to write the last few terms, which is these two terms. Okay, so we have what, so we know implicitly here at the right tail end of the ellipsis we should have another term which ends with f of xn minus 4, right? So that f of x minus 4 and this f of xn minus 4, sorry, not x minus 4, x sub n minus 4, these two together in aggregate forms what, 2 times f of x sub n minus 4. Okay, and we have what we have, plus we have 4 times f of x sub n minus 3. Then we have dealt with this term. Now we have f of, so I forgot to put the closing bracket here. So we have what, f of x n minus 2 over here, and f of x n minus 2 over here as well, right, here and here. So what we can do is we can sum them up to write 2 times f of x sub n minus 2, right? And for the last term, the last two terms, we have 4 of f of x n minus 1, and we have lastly we have f of xn, right, where xn is the rightmost or the upper limit of our integral. Okay, so try to notice a pattern. Okay, so let's try to notice the pattern here. See that sorry, okay, see that before the uh, x values or the functional values of the x's with odd indexes or odd indices, so for x1, for x3, for xn minus 3, for xn minus 1, so we know for sure that n is an even number, right? So n minus 1 will for sure be an odd number, n minus 3 will also be an odd number, right? So before the x values or the functional values of the x's with odd indices, we have 4 multiplied, right? Here, 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 and here, right? So what we can say is, okay, let's try to capture the pattern in a more compact form. So let's say we can rewrite this as something like h by 3 times. So the first term will remain as it is, x0, plus we can say, okay, 4 times summation of f of xi, where I is of course written in subscript form, indicates the index of the x value. Okay, so from I equals 1, starting from 1 up to what? Up to n minus 1, right? So we see that in the second last term over here, up to n minus 1. So if we say that I is this value or the index of I is odd, so I'm running out of space here. So if the value of I is odd, and from starting from 1 to n minus 1, if the value of I is odd, we multiply the functional value of x sub I with 4. Okay, fine. So let's try to capture other patterns that are present in this, other obvious patterns that are present in this expression over here. So notice that in with the functional value of the x values with even indices, for example, for in the case of x sub 2, x sub 4, x sub n minus 4, x sub n minus 2, we have what, 2 multiplied, right? So here, 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 and here, right? So we for sure know that the value of n is even. So n minus 2 is of course an even number. N minus 4 will for sure be an even number as well. And we know that x2 and 4 are even numbers, right? So what we can do is, okay, we have seen another pattern. So let's write that down in a more compact form. So we can write, okay, 2 times I starting from what? Starting from 2 up to what? Up to n minus 2, right? And if the value of I is even, right? So I'm walking on eggshells over here. So if the value of I is even, and if it ranges from 2 to n minus 2, we can multiply the functional value of x sub I with 2, okay, in our compact version of the formula. And then what we have remaining, we have just remaining this term over here. Let's put it in the formula, x of functional value of x sub n, right? Fine. So from this huge thing over here, we have arrived at a more compact and reasonable and easy to remember, easy to recall formula, right? Although I wrote it in a bit congested space, sorry for that. this whole thing over here, box within this red box over here, is our formula for the multi-segment Simpson's 1 by 3 rule. Okay, understood? Fine. So what do we need to know in order to apply this formula? We need to know the step size of our step size of the or the value of h, the step size. We need to know the respective x naught and xi values, the xn value. So we should know the lower limit and the upper limit, of course, obviously. And if we know the step size, we can calculate the respective xi values, right? And if we know the actual function, if it is known to us, we'll be able to find the functional values at those respective points, and simply after plugging them into the formula that we have just derived, we'll end up with an approximation or a multi-segment Simpson's 1 by 3 approximation of the integral. Okay, this is the first multi-segment Simpson's rule that we have just learned. Let's try to now apply it to an example. Let's go back to our presentation and see how we can apply this formula to an example. Okay, fine. Okay, now that we are back to the presentation, so let's proceed. So this whole derivation over here is basically resembles what I have done in the bamboo paper. So after this series of deductions, what we'll end up with this is this formula over here. Okay, so it looks just like the one that we have derived in our bamboo paper, right? So go through this. It's basically the same thing, right? Let's proceed. Now let's try to apply the formula multi-segment Simpson's 1 by 3 rule formula that we have just derived to the same example that we have uh, talked about in our non-composite version of the Simpson's 1 by 3 rule. Okay, the function is the same. This whole function is the velocity function of a rocket that is being launched into space. So we are trying to find the integrand of this function from the lower limit 8 to the upper limit 30 in order to find out the total distance covered by the rocket. Okay, so because we know the integration of the velocity function is the distance covered by a body, right? Fine. And of course, we'll integrate it with respect to dt because the variable here is time. Understand that the variable x here is indicating the integrand value. Okay, we'll try to estimate the value of x now using Simpson's 1 by 3 rule and with n equals to 4 or with using 4 segments. Okay, so notice that we are using 4 segments because 4 is a what? 4 is an even number, right? It's divisible by 2, or it's a multiple of 2, right? So after we find out the integrand approximation using the composite version of the Simpson's 1 by 3 rule, we'll try to find out the true error or E sub t, and we'll again try to find the absolute relative true error and see how it competes with the or how it matches up with the single segment version or the non-composite version of the Simpson's 1 by 3 rule. Okay, fine, let's proceed. Now we know the formula, we know the value of n, we know our lower limit a, we know our upper limit b. We can calculate the step size using b minus a by n. We'll do that and we see the step size is what, 5.5, right? We know the step size is the width of a single segment, right? So we know the width of a single segment. Now we can find the value of each of the t naught up to what, t naught up to we can find the value of t naught, we can find the value of t1, we can find the value of t2, t3 and t4, right? Since we are working with four segments, we need to find the value up to t4. After we find the value of these respective t values, we'll find their respective functional values, right? So which means try to find the value of f of t naught. Okay, so we know t naught is 8, so we need to find the value of f of 8, which is what, if we plug these values into your calculator, we know the actual function. We see that 177.27 meter per second is the functional value at the point 8. We'll do the same thing for what, 13.5, 19, 24.5 and 30 as well. We have found this using just by summing the initial value with the step size. Okay, so 8 plus 5.5 is 13.5. Now we try to find the functional value at 13.5. So we find the respective functional values using our calculator, and then we are ready to plug values to our these functional values to our derived formula, right? So we do that. So in the place of f of t naught, we plug in the value of f of 8 for these respective. So if it satisfies the odd condition, the parity is odd. If the parity is odd, we put the functional value over here. If the parity is even, we put the functional value over here. And lastly, we sum with the we add the entire sum with the functional value at the rightmost limit or the upper limit, okay, which is 30 in the case of this example. Fine. So if we do this using a calculator, what you will end up with is something like what? So 11,061.64 meters. Okay, for the for the approximation of the integration of the given function within the lower limit 8 to the upper limit 30 using what? Using four segments. Okay, where the value of n is 4. Fine. So we have seen analytically, we have found out that the exact value of the integral is 11,061.344 meter. So the true error will be the true value minus the approximate value, which is something like minus 0.3 meters. Okay, so the relative true error will use the same formula just like before, and we see that it's a very minuscule value of 0.0027%. Okay, if we compare this to the non-composite version of the Simpsons 1 by 3 rule, we see that it's a sufficient or a reasonable improvement, right? So we went from 0.0396% to 0.0027% absolute relative true error. So what we have seen is that, okay, if we keep increasing the value of the number of segments, so in the non-composite version we used two segments, right? And we saw that we ended up with a absolute relative true error of, or an epsilon sub 3t value of 0.0396%, right? So as we increase the value up to 2, if we scale up the value up to 4, 6, 8, and 10, we see that the value of the absolute relative true error is gradually decreasing, right? As we are increasing the value of n, right? So we say that, okay, if we increase the value of n, the lesser and lesser error that we, the lesser and lesser error we encounter, right? Fine. So a good rule of thumb is, in order to increase the in order to increase the precision of our approximation, or sorry, not precision, in order to increase the accuracy or the exactness of our the goodness of our approximation, we can choose to increase the number of segments that we are considering for the multi-segment Simpsons 1 by 3 rule. Fine. Okay, if you have any questions, you can let me know about this. Let's proceed to the next topic, which is Simpsons 3 by 8 rule. Okay. Okay, so the naming convention of these algorithms, or these numerical methods of integration that were invented by Simpson is what? As I've said before, it was due to the leading coefficient of the formula that we are deriving, right? So in the case of Simpson's 1 by 3 rule, we see there is an implicitly there is a 1 by 3, there is a 1 by 3 fraction multiplied with this whole formula right here, both in the case of the non-composite version and in the case of the composite version, right? So in the composite version you also see a leading factor of 1 by 3, right? So in the case of Simpson's 3 by 8 rule, what we'll see in a bit is that we end up with a leading factor of 3 by 8, which is why the naming convention is like this. Okay, so in the case, let's try to understand the concept behind the Simpsons 3 by 8 rule. So the idea is that instead of a single order one order or two order polynomial, we'll use a first order or second order polynomial, we'll use a what? Third order polynomial, which is denoted using f sub 3 of x. Okay, so in order to end up with the third order polynomial, we need to consider what? 4 points between the within the limits, right? So we know that from our root finding algorithm, when we learned about our interpolation and root finding algorithms, we learned that, okay, in order to come up with an nth or with an nth order polynomial, we needed n plus 1 data points, right? So in order to come up with a third order polynomial, we need 4 data points, and the 4 data points need to be equidistant, okay, which means they need to be equally spaced. Okay, so in order to make sure they are equally spaced, what we can do is, okay, let's try to partition the whole interval into 3 equal segments, which means we end up with 4 data points that are equally spaced from one another. Okay, fine, equidistant from one another. So In the case of the Simpsons 3 by 8 rule, we say that okay, the area under this third order polynomial within the limits a and b is a good approximation, or an approximation of the area under the original curve f of x, okay, or the integral value of f of x with respect to dx from the lower limit a to the upper limit b. And we know the general format of the general second order polynomial is written by using this thing over here, which is a naught plus a1x plus a sub 2 x squared plus a sub 3 x to the power 3, or x cubed, right? This is the general form of the third order polynomial, right? So there is a typing mistake over here. It should be third order polynomial instead of second order polynomial. Okay, fine. So let's see what the intermediate points look like. So we'll derive it in a bit. So it will be 2a plus b by 3 and a plus 2b by 3. Okay. So let me draw your attention to this slide. There is a text dagger sign over here, right? So you can uh, choose to skip this slide if you want, but if you want to understand how the formula comes about, you can follow along. Okay, but this slide of the derivation part is not important for your exam. Okay, fine. Let's try to see what we can do. Okay, so we know the general form of the third order polynomial is this thing over here. We can express it using vector form, right? So if we multiply this row vector with this column vector, we end up with this polynomial, right? Fine. So we know that in order to find out the four unknowns a0, a1, a2, and a3, we need to somehow come up with what? Four equations, right? So how can we do that? We know for sure that our polynomial, third order polynomial, passes through these 4 points, right? So we know the value coordinates of these 4 points. So we plug them into we plug them in to our equation of the third order polynomial, and we end up with these three equations. Okay, so f of x naught equals to a naught plus a1 x naught plus a2 x naught square plus a3 x naught to the power 3. So there is another typing mistake over here. It will be x naught to the power 3, x1 to the power 3, x2 to the power 3, and x3 to the power 3. So just forgive me for this. When I upload the slide, I'll correct them. Okay, fine. So with these four equations, we can solve them. So we can basically transform them to their matrix form that looks something like this. So we know the unknowns will be in this column vector over here. We are coefficients a naught, 1, x naught square, and x naught cube will be the rows of for the first equation. It will be in the first row. For the second equation, it will be 1 x1 to the power 2 and x1 to the power 3, which will be the second row of this matrix, of this coefficient matrix, and so on. We can form the third row and the fourth row. Now that we have, let's denote this thing using what? Let's denote this thing using, so they denoted it using a. Let's, for the sake of consistency, let's denote this thing using capital A. Let's denote this thing using capital B. And we know our functional values, the vector column vector of our functional values, which is this thing over here. So let's denote this column vector as f. Okay, so we know that the equation here is a times small a is equals to f, right? So our target is to find out the unknown values, or the parameter values, right, or the coefficient values. So what we can do is we can basically say, okay, I don't have space over here, let's write it like this. So a is basically a inverse times f, right? So they have already shown this thing over here. So we know that the matrix capital A times small column vector small a is equals to the column vector small f. So how can we find out the column vector small a, which consists of all my coefficient values starting from, so it will of course be a naught to, there are a lot of typing mistakes here, right? So sorry for that. So these things will be 0 up to from 0 to 3. So what we have, a inverse times the column vector f, right? So that's how we can find out the column vector a. Fine. So now that we know the values of our unknown coefficients, we can plug them into our original general format of our third degree or third order polynomial, and we'll be good to go, right? We have seen that these things are really hard to calculate using hand, right? Let me switch back to the laser pointer. These things are really hard to calculate using hand, especially if we are trying to come up with a symbolic expression, right? Instead of just plugging in the actual values. So what we can do is we know these values. So for x naught, it will for sure be the lower limit. Our x naught will be one step ahead of a. So it will be a plus b minus a by 3. So if you perform the correct algebra over here, you'll end up with 2a plus b by 3. We know our for the point x2. So let's go back to the figure. So x2 is somewhere over here. So here. So x2 will be what? Two steps or two step sizes ahead of the initial point a, right? So it will be a plus 2h, which is what? A plus 2b minus 2a by 3, because we're simply multiplying b minus a by 3 with 2, right? So we end up with a plus 2b by 3. And for the last x value, which is basically essentially the same as a, right? It's the same as b, right? So how can we do that? We say that okay, that x3 is three steps ahead of my initial point a, because we're considering three segments, right? So a plus 3h, with each segment having a width of h, and we know h to be b minus a by 3 because the value of n here is 3. And we say okay, a plus 3b minus 3a by 3 is what? B, right? So the 3 cancels each other out, and a cancel each other out. We end up with just b, right? Fine. So now that we know the value of x0, x1, x2, and x3 in symbolic format, what we can do is we can plug them into this matrix over here, and we'll try to come up with a expression uh, that that basically gives me the value of a0, a1, a2, and a3. Okay, fine. So what we can do is, so I have of course skipped that step over here because that will be a very long very long series of calculations. So what you can do is, okay, you can resort to using MATLAB, Octave, Maple, or Wolfram Alpha. These are symbolic equation solvers. Okay, these are software that can solve equations for you. So you can just provide them with the matrices and the equations and the corresponding f of column vectors, and they will give you the actual values of a naught, a1, a2, and a3 in symbolic format. Okay, just like we have seen in the case of the non-composite version of the Simpsons 1 by 3 rule. Okay, so for just the simplest case of the Simpsons 1 by 3 rule, it was very huge, right? So of course it will be something like that in this case as well. Okay, for the Simpsons 3 by 8 rule as well. So I will left it out of the slide for brevity. So what you can do is you can plug them into the third order polynomial, and and after doing that, we'll integrate that third order polynomial from the lower limit a to the upper limit b, because we are trying to approximate the value of the area under the original curve using the value of the area under the third order polynomial, right? Third order f sub 3 of x, right? So you can trust me that after a series of simplification steps, we end up with this formula over here, which is b minus a times f of x naught plus 3 times f of x1 plus 3 times f of x2 plus 3 times f of x3, this whole thing divided by 8. Okay, where x naught, x1, x2, and x3 are of course these points over here. So x naught is a, x1 is 2a plus b by 3, x2 is a plus 2b by 3, and x3 is b over here. Okay, and we know the corresponding functional values of these points as well. We can plug them in over here and end up with the formula. Okay, and since we know our step size to be b minus a by 3, b minus a can simply be rewritten as what? 3h, right? So we plug in 3h over here, and we take this denominator 8 to the front. So what do we see? We see that the formula becomes, or the approximation of the integrand in the case of Simpson's 3 by 8 rule becomes something like what? 3h by 8 times f of x naught plus 3 times f of x1 plus 3 times f of x2 plus 3 plus f of x3. Okay, and we know Simpson's nomenclature or naming convention is whatever his formula has at the front, right, as a factor, as a constant factor. So in the case of Simpson's 3 by 8 rule, we see that we have a leading constant factor of 3 by 8. So we call this method the Simpson's 3 by 8 rule. Okay, so this is one way of deriving the formula for the Simpsons 3 by 8 rule. There are several other approaches in our lecture note PDF that was written by Professor Arthur Cow. You can go through that if you're interested, but for your exam, that those approaches or those derivations are not important. Okay, you just need to remember this formula over here. So the pattern is pretty simple, right? So x naught, x1, x2, x3, those functional values, we have 1, 3, 3, 1, right? And we are multiplying it with 3h by 8. So very simple to remember, right? So if you practice some relevant examples and maths with pertaining to this formula, inshallah you'll be able to remember it. Okay, fine. Let's proceed. Let's try to simply use the formula that we have derived just now in order to solve an example, okay, or the same example that we have been talking about so far. Okay, so the example is the same. We're trying to calculate the distance covered by a rocket from time t is equals to 8 seconds to time t is equals to 30 seconds. Okay, so this whole thing is the integral of this function over here, this velocity function over here. Now this time we'll use the Simpson's 3 by 8 rule, okay, in order to approximate the integral. Fine, let's see how we can do that. Understand that this is a non-composite version. We'll of course talk about the multi-segment version of the Simpson's 3 by 8 rule as well. Okay. Okay, let's do the non-composite version at first. So we know the value of A, we know the value of B. We can find the value of H by plugging in the corresponding values to this formula over here, B minus A by N. So we know in the non-composite version my value of N is 3 because we are working with 3 adjacent or 3 consecutive segments, right? We are partitioning the whole interval into 3 segments, right? So we have H equals to 0.73333 recurring, right? Fine. We know the actual function, the velocity function. We know the formula that we have just derived. Okay. Now the first state of affair is to find out the t values. Okay, so t naught is obviously the lower limit, which is 8. T1 is one step ahead of t naught, which is 8 plus 7.33, which is 15.33. T2 is t naught plus 2h, 22.66. T3 is t naught plus 3h, which means it is 3 steps ahead of the initial point, which is 30. And our last point T3, which is the rightmost limit or the upper limit, which is what? T3 was 30, right? Fine. So we have already calculated 30. Fine. So okay, so now that we have our ti values or t0, t1, t2 and t3 values, we can proceed to use our calculator and find out the f of t values, right? So for f of t0 we have 177 point something, for f of t1 we have 372 point something, for f of t2 we have what, 608 point something, and for f of t3 we have 901 point something. We have the functional values, we know the value of h. Now we can simply use this formula over here and find out our approximation of integral. Okay, let's do that. So we know 3 by 8 times h is 7.33, and we have already derived these functional values. We put them in their respective place. We see that what we end up with is something like 11,063.3104 meters. Okay, so our actual value was, if we solve the whole integral, this whole integral analytically, we end up with an exact value of 11,061.34 meters, right? So what you can do is, we have already calculated the error values, the true error values and the absolute relative true error values ad nauseum, right? We have done it many times, so we can you can should by this at this point you should be able to do it yourself. So I have provided you the exact value and the approximate value. You can simply proceed to find the error values at your own behest. Okay, I have omitted that part out of the slide for the sake of redundancy. Okay, fine. For the sake of avoiding redundancy, fine. Okay, now let's proceed to the next part of this lecture, which is the multi-segment version of the Simpson's 3 by 8 rule. Okay, this is the composite version. So the idea is simple. So instead of using one third order polynomial in order to approximate the area under the curve, we'll use what, multiple uh, third order polynomials in order to approximate the area under the curve. Okay, if you look at this figure over here, this is the graph of the function. This function x to the power 4 plus 3x squared plus x plus 1. So we are using what, 1, 2, 3, 4, 5, 6, 7, 8, 9. We're using 9 segments to approximate the area under this curve using multi-segment Simpson's 3 by 8 rule. Okay, so the value of n is of course 9, and they have given an extra notation m equals to 3. So m, you can consider m to be a sub-interval. okay, or a greater segment, okay, not the smaller segment that we're talking about. So M is basically this yellow part, green part, and red part, and this green part over here. Okay, fine. And we know the step size to be what? B minus A by N, right? So we know our upper limit to be so 0.6, our lower limit to be minus 1.2. So we can say 0.6 plus 1.2 divided by 9. That thing is our step size. Okay, fine. So let's try to derive the formula for the multi-segment Simpson's 3 by 8 rule. The idea is simple: to approximate the integration of f of x with respect to dx from the lower limit a to the upper limit b, we'll simply calculate the area under the curve of the obtained third order polynomial within the same limits. And in order to do that, for the multi-segment, the composite version, we don't do this. We find out different third order polynomials, right? So within the limits a to x3, x sub 3, so within the limit, so this is our lower limit, which is the leftmost limit, which is x naught, or a, we can also call it a. And we are using three consecutive segments, right? Three adjacent segments. So from x naught to x1, from x1 to x2, and from x2 to x3, these three segments will be at the behest, or will be predicated on our will be predicated on our first third order polynomial. Okay, so the area that we are trying to calculate for this segment will be the area under the curve that is being that is being formed using these 4 points. Okay, so we know in order to come up with a third order polynomial, we need to use 4 points, right? So we will use this point, this point, this point, and this point to come up with a third order polynomial, and we'll try to calculate the area under that third order polynomial in order to approximate the area under the original curve from this lower limit to this upper limit. Okay, we'll repeat the same process for these three segments and these three segments as well. So let's, in the general form, let's try to derive the formula in the general case. So this thing obviously goes from x0 to x9. We are using what, 9 segments, right? So let's see what the formula becomes when we use n segments. So another obvious observation is, since for the non-composite version of the Simpson's 3 by 8 rule we use three consecutive segments, for the multi-segment Simpson's 3 by 8 rule, whatever value of n that we choose, that has to be a multiple of 3. Okay, that has to be divisible by 3. Okay, so in this example over here, we are seeing that they have used 9 segments, right? So 9 is of course our value, multiple of 3. So why does it have to be a multiple of 3? Because we are using three consecutive segments in order to find these partitions or these sub intervals area, area under the curve, right? Fine. So let's go to our bamboo paper and see how we can derive the formula for the multi-segment Simpsons 3 by 8 rule. Okay, fine. Okay, so let's go to the next page. Okay, I'll try to draw the figure here a bit smaller because it takes up a lot of space, right? As we have seen from the last page. Okay, let's draw another figure, similar figure, but this time we'll be using multiple segment Simpsons 3 by 8 rule. Okay, so let's say this is our lower limit, this is our upper limit. Okay, now let's say our target is to partition this whole interval with numerous segments, right? But the total number of segments has to be for sure a multiple of 3. Okay, because single application of the Simpsons 3 by 8 rule mandates that we need to work with three consecutive segments, right? So I'll just put dot dot here. This means that there are many other segments in between them. And let's try to draw the last few segments. Let's say this, and roughly something like this. Okay, fine. So let's try to label this x values. So this will for sure be x naught, right? This is our starting x value. Then this thing will be x1, this will be x2, this will be x3, and let's try to do the same thing for the last few labels. So this will for sure be xn because we are working with n segments. This will be x of xn minus 1. Let me write it a bit more clearly. This will be x sub n minus 2, right? And this will be x sub n minus 3. Fine. So now we know how to label these x values, right? So let's see how the Simpsons 3 by a single application of the Simpsons 3 by 8 rule will work. So let's say, okay, so since we are working with three consecutive segments, we'll first work with this segment, and this segment. Okay, so for working with this segment, these three segments, we need to consider this data point, this data point, this data point, and this data point, right? So we have four data points, and our target is to pass a third order polynomial through all these four data points. And we know that a polynomial of order n that passes through all n plus 1 data points is for sure guaranteed to be unique, right? Fine. So let's say our third order polynomial that passes through all these 4 points roughly looks something like this. Okay, this is of course not an accurate representation. Say roughly looks something like this. Fine. So okay, now that we have worked with the first three segments, our target is to find the area underneath the third order polynomial valid between what, x naught and x3, right? So let's say the area looks something like this. So we say that, okay, the area of the original curve under this subinterval is approximately equal to, or that exact value, or this green shaded region is an approximation of that exact value. Okay, in other words, the green shaded value is the area underneath the what, third order polynomial f sub 3 of x that we have just come up with by fitting it through these 4 points. And this thing drawn in black is our original function f of x. Okay, fine. So we'll do the same thing for the uh, second triplet of segments, second three consecutive segments, let's say. So for that, we'll consider this data point, this data point, this data point, and this data point. And another third order polynomial has to be fit through these four data points. Let's say it looks something like this, roughly like this, right? And the area underneath this third order polynomial is a rough approximation of this subintervals area underneath the area underneath the original curve within this subinterval. Okay, starting from x3 up to what, this is x4 obviously, this is x5, and this has to be x6, right, x sub 6. So another thing to notice is that what we are doing, since we are working with three consecutive examples, we are our each of our what tuple of or a group of segments is starting with what, starting with indices and ending with indices of x values that are divisible by 3, right? So from x naught to x3 we are performing one application of Simpson's 3 by 8 rule, the non-composite version. Again, from x sub 3 to x sub 6 we are applying another instantiation of the Simpson's 3 by 8 algorithm, the non-composite version. Again, for the last few segments, let's work with the last few segments and see what happens. Uh, so we know that we need to work with three consecutive segments, right? So, and we know our value of n for sure to be a multiple of 3, right? So n minus 3 will also be a multiple of 3. So we'll work with this data point, this data point, this data point, and this data point, right? We'll pass a third order polynomial between these data points. Let's say it looks something like this. And this is our another f sub 3 of x, another third order polynomial. Okay, so I forgot to label this. Let's label this one. So it was orange color, right? this is f sub, my bad, f sub 3 of x. So all of these are our third order polynomials. Okay. Okay, let's go back to our previous color. Okay. So what do we do now that we know the third order polynomial that passes through these four consecutive points? We say that the area underneath the curve, the original curve of x, for this subinterval from xn minus 3 to xn, we say that a rough approximation of that area is the area that we have shaded using purple over here. Okay. Now, if we sum up all of this area area values that we have calculated for each of these consecutive adjacent three segments, we end up with the actual approximation or the actual or the final approximation, the aggregate approximation of the multiple segments Simpson's 3 by 8 rule. Okay. So mathematically, you can express it as something like this. If we say that the integrand I is our, let me write it a bit more clearly. So integrand I is our integration from a to b of our function f of x, the original function with respect to dx. Okay, we say that a good approximation of that will be what? The summation of the function of the second or third order polynomial f sub 3 of x. We're talking about this polynomial over here, the first one, from what? From the lower limit x naught, which is essentially a, to the upper limit, what? X3, right? X sub 3. Since we're working with three consecutive segments, we are working with x. We are working with a lower limit x naught and upper limit x3. Okay, and this we have to write dx over here plus what we have from x3 to x6. We'll work with the next three consecutive segments. My bad. So this will be x3 up to x6. We are working with another third order polynomial. We'll integrate it, or we'll try to find the area underneath that third order polynomial. And since there is no more space, let's write ellipsis over here, and let's write the last two terms. Okay, so the last two terms will look something like what? So for the last term, we'll work with what? Xn minus 3 up to xn, and for the second last term, we'll work with xn minus 6 up to x minus n minus 3, right? Fine. So let's write that down. So from xn minus 6 up to xn minus 3, these are our limits. We'll try to find the integrand of third order polynomial that passes through each of these coordinates that I have marked with purple color. And for the last term of this whole summation expression, we have what? Xn minus 3, from xn minus 3 up to xn, which is essentially the same thing as b. We'll try to integrate another third order polynomial. So sorry, I have said for this one, I have not drawn it over here. So for this term over here, it will be the shaded region purple. Okay, so these are the function, these are the respective data points of the coordinates through which we need to pass this third order polynomial. Okay, for these four data points, we end up with a third order polynomial. So we'll try to find the integration of this third order polynomial with respect to dx from xn minus 3 up to xn. Okay, fine. So this whole summation thing will approximate our actual integrand value from the lower limit a to the upper limit b. Fine. So now that we have found out the separate terms, separate integration terms, we'll use the formula that we have derived, the non-composite version of the 3 by 8 rule formula, okay, for each of these terms. So let's do that. Now we have plenty of space. Let's try to utilize it. Okay, so for this term over here, what do we have? If you recall, the formula looked what something like what? So it would be the disparity between them, x3 minus x naught divided by 8, if I recall correctly, uh, times what? F of x naught. Then there was 3 times, and I did a bit more clearly, x naught plus 3 times f of x1 plus 3 times f of x2 plus f of x3, right? So if you recall, this was our formula for a single application of the Simpson's 3 by 8 rule. Okay. Now that we have done it for, let me write it a bit clearly over here. This will be x naught course. Okay. X naught. Okay. Fine. Now for the second term over here, it ranges from what? X3 up to x6, right? So let's do that. Uh, so we have x. Let me utilize this space over here. So let's write from here. So from this we are starting from here again. We have what? X6 minus x3 divided by 8 times f of x3 plus 3 of, sorry, 3 times f of x4 plus 3 times f of x5, and lastly we have f of x6, right? Fine. Okay, and let's put some dot dots or ellipses between them in order to avoid redundancy. And let's work with the last two terms. Okay, so for the second last term, what do we have? We have xn minus 3 minus xn minus 6 divided by 8 times what? What do we have? We have f of xn minus 6 plus f of xn minus 5. So this will be multiplied by 3, my bad. 3 of 3 times f of xn minus 5 plus 3 of f 3 times f of xn minus 4 plus f of xn minus 3, right? So I'm starving for space here. Okay, fine. So okay, so now that we have the second last term, let's write the final term over here. So for final term is the application of the same non-composite version of the Simpson's 3 by 8 formula for this term over here. Okay, so let's do that. So what do we have? Xn minus xn minus 3. Okay, so xn is the label of our last x value minus xn minus 3, x sub n minus 3 divided by 8 times f of x sub n minus 3 plus 3 times f of x sub n minus 2 plus 3 times f of x sub n minus 3 plus what? Last term, right? F of xn, functional value at the upper limit, right? The value b. Fine. Okay, so now that we have completed writing the expanded version of all of these terms after applying the formula, our job is to find out a more compact representation of the formula for our benefit. Okay, let's see how we can do that. So in order to do that, we need to perform some simple algebra. So notice that x3 minus x naught, so x3 minus x naught is what? 3h, right? Because this whole thing over here has a breadth or a width of 3h. So my color choice is very bad over here. Let me write it using a proper color. So this thing over here is 3h because the width of each segment is h, right? So the distance between x0 and x3 is 3h. So we can generally write it as something like this, that xi minus xi minus 3, where I is for sure a value that is divisible by 3, will be 3h, right? So applying this thing over here, we can say, okay, let's write this as 3h. Let's write this as 3h as well. Let's write this as 3h as well. So we know that our n, the n that we are selecting, the number of segments that we are deciding to use, is for sure a multiple of 3, right? It's divisible by 3. So that means, that implies that n minus 3 is also divisible by 3, and n minus 6 is guaranteed to be divisible by 3 as well. Okay, so the difference between them will for sure be 3h, and we can say the same thing in this case as well, 3h. Okay, so what we are seeing is that there is a 3h by 8 factor that is common for all of these terms, right? So we can factor it out for our benefit, right? So let's do that. So we can write it as something like 3h by 8, right? Fine. Now whatever we will do, we'll do it within the third bracket. Okay, fine. So let's try to write down the remaining terms, which is f of x naught plus what we have, 3f of x, 3 times f of x1, plus we have 3 times f of x2, plus, okay, notice that for this f of x3 term over here, we see an occurrence of f of x3 over here, as well as in the first term of the next term, right? Of the next, by term I mean this whole thing over here. So in the first part of the next term, we see another occurrence of f of x3, right? So we can write it together in aggregate as 2 times f of x3, right? Good. So now that we have written this, what do? We can do what? We can proceed, right? We can proceed with the next term, which is what? So we have worked with f of x3. Now let's work with f of x4, which is this thing over here. So we'll write 3 times f of x4 plus, um, then we have what? 3 times f of x5 plus f of x6, right? Fine. So notice that, again notice that f of 6 is being uh, is present over here and implicitly present in another, in the first part of the following term as well, right? So we can write this thing as 2 times f of f6 over here, right? So let's write it a bit clearly, 2 times f of f6 again. So for the intermediate terms, let's write dot 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 over here for brevity, and let's work with the last two terms. Okay, so again 3h by 8 has been factored out. We have what? So implicitly we had what? And sorry, simply what's happening? Okay, so implicitly we had f of x n minus 6 term over here, right, in the last part of the uh, preceding term, right? And we have another f of x n minus 6 over here. So these two will together form 2 times f of x n minus 6. Okay, fine. And let's write down the remaining term as they are, 3 times f of x n minus 5 plus 3 times f of x n minus 4 plus, again we do the same thing for f of x n minus 3, right? It, one time it's appearing here, and another time it's appearing here, right? So these two together form 2 times f of x n minus 3, right? Fine. Okay, then we have 3 times f of x n minus 2. We have 3 times f of x n minus 3. Oh, this should be f of x n minus 1, right? So mistakenly I have written 3 over here. N minus 1, And lastly we have f of xn, where xn is our upper limit, right? Let's close this parenthesis. Fine. So that's a huge expression, right? Let's try to boil this down further to a more compact and concise version of the formula. So in order to do that, we need to basically identify some patterns and try to use the summation notation in order to make it shorter. Okay, so let's do that. So notice that for the values of x's with the subscripts or the indices that are what, one. So let's choose a good color, that are 1, 4. Then we have xn minus 5. Then we have what, xn minus 2. Okay, so what we have seen here is that if the uh, modulus value of the index, so if we divide the value of the index by 3, the remainder that we get is for sure 1, right? So if we divide 1 by 3, or if we perform 1 mod 3, so 1 mod 3 is equal to 1, right? Again 4 mod 3 is equals to 1, right? Then we know that n is a multiple of 3, right? N is divisible by 3. If we subtract 5 from it, 5 is basically 1 less than 6, right? Since we're subtracting 5 from it, we can for sure say that this subscript or this index over here, so if we perform n minus 5 mod 3, we will for sure get a value 1, right? So if we say the value of n is 12, right? 12 is a value that is divisible by 3 for sure, right? So 12 minus 5 is 7. 7 mod 3 is what, 1, right? If we divide 7 by 3, we are bound to get a remainder of 1, right? Fine. So that is one pattern that we have discovered. So the pattern that we have seen is that, okay, there are two consecutive terms that are being multiplied by 3. If we only consider the first of those two consecutive terms, we see that the subscript of the x values are subscripts or indices that when divided by 3 yields a remainder of 1, right? So let's try to take advantage of that pattern. Okay, so firstly, okay, let me choose the black ink first. So firstly, what do we have here? We have 3h by 8. This whole thing has been factored out, this thing. We have f of x naught plus, so we have seen that, okay, 3 times summation of f of xi, or functional values of xi, where I starts from 1 and ends to n minus 2, right? And the condition is what? I mod 3 is bound to be 1, right? Or when I is divided by 3, the remainder will for sure be 1. Fine. So now that we have done this, we have took care of these terms, right, that follow this pattern. Now let's see what we can do for the second of these two consecutive terms. So let's choose a different color. Okay, so notice that when we multiply the second term of these two consecutive terms, the subscripts are what, 2. Subscripts are what, 5. Again it is n minus 4 in this case. Again it is n minus 1 in this case. Okay, so when we divide 2 by 3, the remainder that we get is 2, right? Or 2 mod 3 is 2, right? Again 5 mod 3 is also 2, right? N minus 4 mod 3. So let me try to write it over here. 2 mod 3 is 2. 5 mod 3 is 2. Then we have a general term n minus 4 mod 3. This will for sure be 2. Let us verify this claim by using like by taking the value of n to be 12. So 12 minus 4 is what? 8, right? So 8 mod 3, what do we have? We have a nearest multiple of 6, right? So 8 minus 6 is 2, so the remainder is 2. Again for n minus 1, let's try to verify that. Let's again use the value of 12. 12 minus 1 is 11. 11 mod 3 is what? 2, right? Because we have what? 3 times 3 is 9 and 11 minus 9 is 2, right? So for these terms, so the second of these two consecutive terms, we are seeing that the indices when divided by 3 yields a remainder of 2, right? So okay, let's take advantage of that pattern again and write something like this: 3 times summation of f of xi values, or the functional values at the point xi, where I starts from where? I starts from 2 up to n minus 1, such that the condition is that the value of I, or the index value, has to yield a remainder of 2 when divided by 3. Okay, in other words, I mod 3 has to be 2. Okay, so I'm running out of space yet again. So this thing is I mod 3 equals to 2. Okay, that's the condition. And lastly, what do we have? We have taken care of this thing. We have taken, so that it's not appropriate to cut it. Let's try to use a different color. So we have taken care of this term over here using this. We have taken care of these terms, where these terms, these and these terms using this thing over here. Then we have taken care of the second of these three multiplied terms. Okay, so my bad. So these terms, this term, this term, and this term is represented using this term, right? And the second of these three multiplied terms is this one, this one, this one, and this one is represented using this term over here, right? Now what do we have remaining? We have only this isolated last term remaining, right? F of xn. We simply place it into our formula, and then we are good to go. Okay, so we have f of x sub n. Fine. So this thing is much more compact and easy to remember, right? So we have what? Ultimately, we end up with a formula for the multi-segment Simpson's 3 by 8 rule, which looks something like 3h by 8 times f of x naught plus 3 times summation of f of xi values from starting from I equals to 1 up to n minus 2, such that I mod 3 is equals to 1 plus 3 times I functional value summation of the functional values of xi, where I starts from 2 up to n minus 1, such that the modulus value, or the I mod 3 is equals to 2, or the remainder value of the division between I and 3 is 2. Okay, and lastly we have the last term f of xn, and that's the formula for our Simpson's 3 by 8 rules composite version. Okay, so notice that we still have a 3 by 8 leading constant factor, right, for the formula. That's why the naming convention is multi-segment Simpson's 3 by 8 rule. Okay, so these derivations are pretty important for your exams. Try to practice them at your own behest. Okay, fine. So now that we know how to derive the formula for the composite version, the multiple segment Simpson's 3 by 8 rule, let's try to apply this formula to the same example we have talked about throughout this lecture and see how it works. Okay, let's go back to our presentation. Okay, now that we are back to the slide, so this formula over here should just, oh sorry, my bad, I think I forgot this term over here. So let's go back to our bamboo paper and amend our derived formula. Okay, I did a small mistake, so let's go back to our bamboo paper and see what mistake that I have made. The mistake that I have made, let's try to correct it. Okay, okay, so I forgot to deal with this term, these terms that are being multiplied with 2, right? So let's do that. Okay, so notice that when our subscript is 3, 6, um, n minus 6, n minus 3, the corresponding functional values of those x values is being multiplied with 2, right? So here, 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 right? So what can we say about these terms? We can say that these values, these subscript values, the index values are multiples of 3, right? Which means when I multiply the value of these indices with 3, I should expect a remainder value of 0, right? Because when we perform the modulus operation between a multiple of a number and that number itself, we end up with the value 0, right? Fine. So to show it more explicitly, let me write down the modulus values just like before for the sake of consistency. We know 3 mod 3 is 0. We know 6 mod 3 is 0. We know n minus 6 mod 3 is 0. So why is that the case? We know the original value of n to be a value multiple of 3. So let's take the value of 12 as our verification example. So 12 minus 6 is what? 6. 6 mod 3 is 0. So we know whatever value we take for n, if it is a multiple of 3, and if we subtract another multiple of 3 from it, which is 6 in this case, it will for sure be divisible by 3 value, right? The difference will of course be divisible by 3, and the modulus operation with 3 will yield a value of 0. And same can be said for n minus 3, right? N minus 3 mod 3 will also be 0. Fine. Now that we know these facts, let's try to use the pattern that we can uh, basically milk out and try to see what the compact version of the actual formula looks like. So whatever I have did just a while ago was wrong. Okay, I forgot to deal with this 2 multiplied terms. Okay, so 2 multiplied by what? The functional values of f of x sub I starting from I equals to what? 3, right? 3 up to n minus 3, right? N minus 3, and the condition is that the value of I, or the index value of the subscript values, when modded with 3 and when the modulus operation with 3 is done, we should expect a value of 0, okay, which means the index values are multiples of 3 or are divisible by 3, okay. Okay, and lastly we have the last term that we have to add, which is this isolated term over here, f of xn, where xn is our rightmost limit or our upper limit, right? Let's box this term just like before, and this is the correct version of my Simpson's multi-segment 3 by 8 rule. Okay, multi-segment Simpson's 3 by 8 rule. Sorry for the earlier mistake. Okay, it's very late at night and I'm very sleepy. So sorry for the mistake. So let's go ahead back to our presentation and try to apply this formula to the same example that we have been talking about. Okay. Okay, so this slide basically discusses how to derive the formula for this multi-segment Simpson's 3 by 8 rule. So whatever formula that we have ended up is something like this. Okay, so follow the derivation from the bamboo paper and try to practice it. Okay, that thing is very important for your exam. Fine. So now let's try to apply that formula to the same example that we have been talking about so far. So that's the integral that is giving us the distance covered by a rocket that's being launched into space. Okay, so within the time t is equals to 8 seconds to t is equals to 30 seconds. Okay, fine. This time we'll use the say composite Simpson 3 by 8 rule, and our value of n is 6. Okay, so we are using 6 segments, and notice that the value of 6 is of course what, divisible by 3, right? So whatever value of n that we choose, that has to be divisible by 3 in order for this method to work. Okay, fine. So we know our function, we can calculate the step size because we know our upper limit and our lower limit. So we do that p minus a by n is 6, as I've said before, we get 3.66. Okay, and we know the value of t naught, which is 8. So our next job is to find the value of t1, t2, t4 and t5 and t6, right? since we're working with 6 segments, we have to calculate up to T6. And how do we do that? We just add h with t naught in order to get h1. We add 2h with t naught in order to get t2, because t2 is 2 steps ahead of t naught, right? And so on. We follow the same pattern in order to calculate t3, t4, t5, and t6. Okay. After we calculate these values, we calculate their corresponding functional values, because you already know the function. We just plug in the respective values in order to find out the corresponding functional values, and we get something like 177 point something, 270 point something, and so on. Okay, up to 6,000. This thing will be what, there will be a comma over here, right? So lot of typing mistakes in today's slide. So 30 comma 901.66740. Okay, so these are the corresponding functional values. So now that we know the corresponding functional values, we know the upper limit, the lower limit, and the value of h, we can simply use our formula and plug in the functional values at their respective slots. Just just have to check whether the condition is being met or not. So for the first condition, we had what, our I values were 1, 4, 7, and so on. That means the value of I when divided by 3 yielded a remainder of 1, right? For the second term over here, we use I values of I equals to 2, comma 5, comma 8, right? That meant that whenever we divide the respective I values with 3, we are bound to get a remainder of 2, right? And for the last and the second penultimate term over here, the second to last term, we are using the values of I as 3, 6, and 9, and so on, right? Which means these are multiples of 3 up to n minus 3, right? Since n is a multiple of 3, n minus 3 will also be a multiple of 3. And the last term is fxn, of course. So we'll use those respective ti values, these are I values. We just have to check the actual condition. Okay, then we'll plug those respective f of x values to the appropriate slots. We just put the values into our calculator and calculate. We should get a value that is approximately equal to 11,601.4696 meters. Okay, fine. So now that we know the approximation of the multi-segment Simpson's 3 by 8 rule, we also know the exact value, which was what I exact was 11,061.34 meters, right? So what you can do is you can calculate the true error and the relative what absolute relative true error, right? Which was denoted using epsilon sub t. You can of course do it since you already know the true value and the approximate value. And you can compare and contrast between the approaches and see which approach performs better. Fine. So how does multi-segment Simpson's 3 by 8 rule how can they be fused? Okay, so there is a we can we can basically combine these two approaches, the Simpsons 1 by 3 approach and the Simpsons 3 by 8 approach, and come up with a composite version of a mixed version of the composite Simpsons rule. Okay, so how can we do that? Let's discuss that. So our target is to find the area under the curve f of x from the lower limit a to the upper limit b, which is the same as saying to find the integral value of the function f of x with respect to dx from the lower limit a to the upper limit b. So the first thing to do is to divide the span b minus a. So our span is from a to b, right? So the length of the span is b minus a, right? The b minus a span has to be subdivided in such a manner so that the sum of the segment or the total number of segments together is a summation of a multiple of 3 and a multiple of 2. Okay, so the common number is something like what, 5 or 7, right? So if we take number of segments to be 5, we can use so let's go to the bamboo paper and try to visualize it, okay, instead of just talking it conceptual and visual concept abstractly. Okay, let's go to our bamboo paper and visualize it more clearly. Okay, so let's go to the next page. Okay, so let's draw another axis over here. Let's draw the Cartesian coordinate plane over here. It's my sad attempt to draw a straight line. Okay, so let's say our function looks something like this. Our idea, our target is to find out the area under the curve f of x from A to B. Okay, so this is of course f of x. Fine. So what can we do here? So let's say we have chosen the value of the n, or the number of segment n, to be 5. Okay, so 5 is neither a multiple of 2, it's neither a multiple of 3, right? So we are at predicament here, right? So we can neither use the Simpson's 1 by 3 rule, or multi-segment Simpson's 1 by 3 rule, or the multi-segment Simpson's 3 by 8 rule over here, right? When we take the number of n as 5. So what can we do in order to ameliorate this, in order to ameliorate this situation? We can use what the mixed version of the Simpsons rule. Okay, let's see how we can do that. So let's try to eyeball it, and let's try to divide this whole interval into 5 smaller subintervals. So approximately it should look something like this. Okay, 1, 2, 3, 4, 5. So of course these segments are not equal. That's the best that's what I can do by eyeballing it. Okay, fine. So the idea of the uh, composite, the idea of the the mixed version of the Simpsons 1 by 3 and the 3 by 8 rule, the combined version, is that okay, for a particular series of segments, we'll apply the Simpsons 1 by 3 rule, and for another particular series of segments, we'll apply the Simpsons 3 by 8 rule. Okay, so let's see, the simplest form is this, of course, for n equals to 5. So we'll consider the first 3 data points. So for 3 data points, you can pass what, a second order polynomial between these 3 data points, right? It should look something like this, and we calculate the area under this second order polynomial. It should look something like this, right? So this thing over here is f sub 2 of x, of course, right? Fine. Okay, and the next part of the next step of the idea is that okay, now that we have uh, come up with a second order polynomial, let's use the next 4 data points, and apply the Simpsons 3 by 8 rule in order, because our target is to find the area underneath the third order polynomial that we get by passing that polynomial through these 4 data points. Okay, so it should look, roughly should look something like this, and we calculate the area underneath this curve, this polynomial, and we sum these two spaces together, these two areas together, and we say that whatever summation we end up with is an approximation of the area underneath the original curve of x. Again, so that's the idea behind the mixed Simpsons 3 by 8, 1 by 3 and 3 by 8 rule. Okay, fine. So let's try to scale it up to more segments. So let's say instead of n equals to 5, so let's, why not take n equals to 7, right? So how can we say now our value of n is 7? So how can we partition, or how can we uh, permute? Okay, how many permutations of multiples of 2 and multiples of 3 can we use to apply the mixed version of the Simpsons 1 by 3 and 3 by 8 rule? Let's try to visualize that. Okay, so let's say this is another Cartesian coordinate plane. This is our function. This is the upper limit, our lower limit. So this time our idea is to what? Partition this whole interval into 7 segments, right? So 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6, 7, right? 1, 2, 3, 4, 5, 6, 7. So of course the last segment is a bit thicker than the others, but okay, let's try to rectify it. Let's say this is our b value. Okay, let's erase it. Okay, okay. So now that we have chosen the value of n to be 7, we can say okay, so why not use the Simpsons 1 by 3 rule the composite Simpsons 1 by 3 rule for the first three data points, the first two segments. We'll use the Simpsons 1 by 3 rule in order to find this area over here. Then what can we do? We'll say, okay, for the rest of the segments, we'll follow the composite version of the Simpsons 3 by 8 rule. Okay, so we say, okay, we'll use these four data points, 1, 2, 3, 4. We'll use these four data points in order to come up with a third order polynomial that passes through all four data points, and we calculate the area beneath that polynomial within the suitable range, and we say that that's another approximation, that's another part of the approximation. Okay, and again we'll do the same thing for the, so did I get 1 2 3 4 5 6 7, right? So I have what I have worked with already. I have worked with 5 segments, right? Now let's work with the two remaining segments. So what can we do? We say that, okay, I have 2 segments remaining, which means I can work with at most 3 more data points. And we know we can work with 3 data points by applying the Simpsons 1 by 3 rule, right? So using these 3 data points, let's say we come up with a curve that looks something like this. That thing does not pass to the first point. Let's make it pass to the first point. Let's do something like this, and we'll try to calculate the area beneath this third or second order polynomial, and that's another part of the whole sum or aggregate of the approximation. Okay, so what have we done here? We have applied the Simpsons 1 by 3 rule for the first 2 segments. Then we have applied the Simpsons 3 by 8 rule for the middle for 3 segments, and for the last 2 segments we have again applied the Simpsons 1 by 3 rule, right? Now, is there other permutations of the same approach? Yes, there are. How so? Let's try to find that out. So let's say another approach can be something like this, right? So this was our original function. So let's try to get 7 segments by using brute force. 1, 2, 3, 4, 5, 6, 7, right? So this thing is our A, that's our B, our upper limit, and say, okay, so why not apply the Simpsons 3 by 8 rule at first. So my bad, so change the color. So for consistency I am following the same color scheme as I have used in this example. So let's say, why not use the first 4 data points, the first 3 consecutive segments, to come up with a third order polynomial that passes through all of these points, and then calculate the area beneath that curve, okay, in order to approximate the area beneath the original curve within this subinterval. Okay, so we firstly apply the Simpsons 3 by 8 rule. Then what can we do? Then we apply the Simpsons uh, 1 by 3 rule for this data point. Let's say we have a curve that looks something like this. So our Simpsons 1 by 3 method yields this area over here, and for the last 3 data points, or the last 2 segments, so I'm following the same color scheme, this and this point, we have approximated another second order polynomial. Let's say it looks something like this. My bad. So let's say it looks something like this. Okay, so our job is to find the area beneath this second order polynomial, which is this blue shaded region, okay, or cyan shaded region. So if we sum them up, we find the aggregate approximation of the area underneath the original curve. Okay, so what have we done here? So instead of applying Simpsons 1 by 3, 3 by 8, and 1 by 3 in this serial, we have applied the methods using what? So for the first 3 segments, we applied 3 by 8 rule. For the second and third group of segments, which are of width 2h and 2h respectively, we have used Simpsons 1 by 3 rule, right? Then again we can do what? We can apply uh, 1 by 3, 1 by 3, or we can apply the reverse version, right? We can apply 1 by 3, then 1 by 3, then 3 by 8, right? So how many permutations do we end up with? So since we have what? We are working with two methods, so there will be divided by 2, and we have what 3. We are partitioning the whole 7 segments into 4, 2 and 2, right? So 4 plus 2, sorry, 3, 2 and 2, right? So 3 plus 2 and 2 is 7, so we are working with 3 separate segments, right? 3 separate group of segments, right? So our total permutation is 3 factorial divided by 2 factorial, which is what 6 by 2, which is 3, right? So we have 3 approaches. So this is one approach, this is one approach, and another one is this approach over here. Fine. So now that we know how to work with the mixed version of the Simpsons 1 by 3 and 3 by 8 rule, let's try to see what uh, let's try to uh, see how we can step by step dictate the series of actions. Okay, let's go back to our presentation and see the step by step algorithm, basically the algorithm of the mixed Simpsons 1 by 3 and 3 by 8. So formally the algorithm goes something like this. So the first step is to take your value of n that you have set and partition it in such a manner such that the sum of the values that we are partitioning it with are multiples of 2's and multiples of 3's. Okay, so let's say we are partitioning n into n, n1, n sub 1 and n sub 2. Okay, so whatever the sum of n1 and n2 that we have, it will for sure be equal to n. And the second step is to what? To compute the step size, right? So the step size is what? B minus a by n. We know the value of n, we know the value of b and the value of a. We can find the corresponding value of h. And we know each of the xi values, how to calculate them, we already know. So since x naught is equals to a, x1 is one step ahead of a, so a plus 1 times h, and so on. Okay, so xi will be a plus I times h. Okay, and the last step will of course be b, which is our upper limit of the integration, right? The third step is to compute the result from the composite Simpson 1 by 3 rule. So for the multiseg, we at first find out the area underneath the curve for the segments that are that segments above which we are applying the Simpsons 1 by 3 rule. Okay, so we will apply the Simpsons 1 by 3 rules formula, the composite version of the Simpsons 1 by 3 rules formula, and for the respective functional values, we plug in the respective values of the functional values, and we'll calculate the integrand I1, okay, I sub 1. Now we'll do the same thing for the segments or the group of segments that above which we are applying, over which we are applying the Simpsons 3 by 8 rule, the composite version of the Simpsons 3 by 8 rule. We'll use the derived formula that we have derived for the Simpsons 3 by 8 rule, the composite version of the Simpsons 3 by 8 rule. We'll use that formula. We'll use the appropriate functional values at the appropriate slots. And notice that the value of n is now n2 over here, right? Because for the Simpsons 3 by 8 rule, the value of n has to be a multiple of 3. And in this mixed version, the n2 is a multiple of 3 and n1 is a multiple of 2, which is why in step 3 we saw the n is replaced using n1, right? N sub 1. Fine. So now that we have completed step 4, our result of step 4 should be what? I sub 2, right? Which is the integrand for the Simpsons 3 by 8 rule. Now next our job is to sum up I1 and I2 in order to get our aggregate approximation, which is capital I. Okay, the approximate answer for the integrand. Okay, the approximation of the integrand. Fine. This is basically a step-by-step workflow of the multi-segment mixed Simpsons rule. Okay, where we are basically combining the 1 by 3 and 3 by 8 rule. So what happens is that when do we use it? We use it when we see that okay, certain portions of our original function we can approximate it better using a second order polynomial, using a instead of using a third order polynomial. Okay, that's when we use the mixed Simpsons rule. Okay? We basically dissect or scrutinize the whole actual function, and we appropriately allocate which groups of segments we will use. For which groups of segment we'll use the Simpsons 1 by 3 rule, and for which groups of segment we'll use the Simpsons 3 by 8 rule. Okay, that's entirely empirical and observational, and up to the statistician or the guy that is doing the experiment. Okay, fine. So let's try to apply this multi-segment mix Simpsons rule, this whole step-by-step algorithm that we have just learned. We'll try to apply it to the function or the integral that we have been talking about throughout this entire lecture. Okay, which is this uh, the distance covered by the rocket from time t is equals to 8 seconds up to t is equals to 30 seconds. Okay, so this time we'll use the Simpsons 1 by 3 rule for the first 4 segments. So n1 is of course equal to 4, and we'll use the Simpsons 3 by 8 rule for the what? For the last 3 segments. Okay, so n by uh, so n sub 2 is equal to 3. So n2 is a multiple of 3 and n1 is a multiple of 2, of course. So of course we have to, since n1 is 4, we have to apply the Simpsons 1 by 3 rule 2 times, right? So let's see how it is done. Okay, so our segment with this what, p minus a by n, of course n is of course n plus n1 plus n2, which is 4 plus 3, which is 7. So the total number of segments that we have considered for this problem is 7. So 30 minus 8 by 7 is 3.1 for something. Okay, that's our step size. And we know the actual function. We will try to find out the corresponding ti value. So we know the value of t naught. We can find the value of t1, t2, t3, t4, t5, t6, and t7 using the value of h. So we know the ith t is I steps ahead of the t naught or the initial value, and accordingly we'll find out the actual ti values. Okay, so notice that from t naught to t4 we are using the Simpsons 1/3 rule, and from t4 to t7 we are using the Simpsons 3 by 8 rule, right? And we have what, one segment, two segment, three segment, four segment between these 5 data points, and we have one segment, two segment, three segment, four segment between these 5 data points. Okay, so one, two, three segments between these 4 data points. Okay, so for the last 4 data points we are using the Simpsons 3 by 8 rule in order to come up with a third degree polynomial, third order polynomial. And for the what, first 1, 2, 3, 4 segments, we are using the first 5 data points in order to come up with what, 2 separate second order polynomials. Okay, in order to apply the Simpsons 1/3 rule. Now, since we know the ti values, we can find out the corresponding f of ti values just by using our calculator and plugging the respective t values to the f of t function that we already know, and we will end up with these values over here. Okay, you can check them out if you need using a calculator. So now that we know the functional values, we can appropriately place them into the respective slots in the formula. So for the Simpsons 1 by 3 rule, we'll use this composite version of the Simpsons 1 by 3 rules formula in order to find out the value of I1. Okay, since we already know the value of the f of ti values, we can find the corresponding uh, I we can sum them up according to the formula and multiply it with h by 3. We also know the value of h. We multiply it with h by 3 in order to find this I1 value, which is 4364.1197. Okay, and for I2 we need to apply the formula of the Simpsons 3 by 8 rule. We are applying it only once since there are only 3 segments remaining, and 3 segments correspond to 4 points, right? And since we have the last 4 points, we'll use those last 4 points to come up with a third order polynomial, and calculate the area underneath that polynomial in order to approximate the value of the original function within that interval. Okay, within the last 3 segments interval. So the value of I2 with the respective functional values comes up as something like 6,697.3663. So if you notice that this term over here, it says no contribution, right? So look at this term over here. We are in our formula, if you recall, we use the for this term is what, pertaining to the values of the indices which are multiples of 3, right? So I is equals to 3, 6 up to n minus 3. So since our value of n here is 3, we know that if we start with I is equals to 3, and if we end at n minus 3, we end up at basically 3 minus 3 is equals to 0. So none of the functional values are suitable for this slot over here, since our last 3 segments are being considered for. So for our Simpsons 3 by 8 part of this problem, we are considering n equals to 3, right? So this part doesn't contribute anything to the sum. So you can say basically 2 times 0, right? Because this thing is not summing up anything. This is why this is 2 times 0. And if you plug in the respective values into your calculator, you should end up with this value over here. Now we know in our last step After finding the value of I1 and I2, we just simply sum them up in order to get our final approximation, our aggregate approximation, and these two values basically sum up to this 11,061 meters exactly. Okay, so since we know the approximate value now, you can use this exact value that I have written over here for this problem and find out the true error and the relative true error, right? You already know how to do it, and you can compare and contrast this Simpsons 1 by 3 rule, Simpsons 3 by 8 rule, the composite version of the Simpsons 1 by 3 rule, the composite version of the Simpsons 3 by 8 rule, and the mixed version of these two rules. You can compare and contrast them using the error values. Okay, you can see which performs better for this specific example. Fine, so that is all I think for this lecture over here. I have recorded the lecture for both the classes into a single video. So okay, try to take a break between the methods if you think that this lecture recording is too lengthy. You can of course take breaks between the topics. Okay, and just another reminder is that the slides that have been marked with the text dagger, the red text dagger symbols, for example, this symbol over here, those slides contain the contents of those slides are not important for your exam. So of course these huge derivations will not come in your exam because you won't have MATLAB and equation solvers with you, right? So those things will not come in the exam, but it's important for you to understand the flow of the calculation in order to understand how we are deducing the actual formula, right? Which is why I included this part into the slides, okay, just for the sake of completion and for the betterment of your understanding. Okay, so that's all from my side. If you have any questions, ask me in the class or write your questions in the comment section. And yeah, you can also contact me through messenger, WhatsApp, or email. It's up to you, and I'll try to reply it. Okay, and another thing is that everything that I wrote in the bamboo paper, the derivations and whatnot, my handwriting may seem a bit obscure or very bad, right? So what I'm doing is I'm writing all those things using my mouse. Okay, so I don't yet have a graphics tablet, so writing those things using the mouse is very difficult. Okay, if you have experience, you already know about this. Your hand starts to hurt real bad after a specific period of time. So sorry for that if you don't understand, if any part of my handwriting seems unintelligible. You can of course contact me and ask me what those writings mean. Okay, I'll of course answer. Okay, fine. That's all from my side. Okay, assalamu alaikum warahmatullahi wabarakatuh.